All right, so as we look at operations when we're in component form, we've talked about addition and subtraction geometrically. We've drawn them out, okay? But what we're going to do here is we're actually looking at them as components and seeing how to add them without having to draw them out, okay? So you'll notice here, if I'm adding two vectors, I simply add the horizontal components, like we have right here, u plus v, I do c plus a, and that's the horizontal component. And then u plus v, I do a d plus b. That's the vertical component. So I add the horizontal components and I add the vertical components. All right? And by the way, now we can actually prove by looking at this that vector addition is in fact commutative. We saw it geometrically, but if we were trying to prove it, we would have to do something like this. Notice here, now that we have it written like this, inside here, I'm just adding two numbers. And I know that addition with numbers is commutative, so I know I could rewrite this as a plus c. Okay? And I know this, since that's just adding two numbers, I can change the order there, so that's b plus d. So guess what? Now we can see that u plus v is equal to a plus c, b plus d, and v plus u is a plus c, b plus d. Therefore, we just proved that u plus v equals v plus u. We just proved the commutative property for vector addition. Okay? So there's a little, it's actually what's called set theory, or number theory that we're looking at there. Okay? To prove that this works. All right, so let's actually do this once here. We've got vector u and vector v. If I wanted to do u plus v, I'm simply going to take the horizontal components, 4 and 1, and I'm going to add them together. And then I take the vertical components, 3 plus 6, and I add those together, so I get 5, 3 as the vector. If I were to actually sketch this, all right, u goes over 4 and down 3. So here's my vector u right there. And vector v goes over 1 and up 6. All right, so over 1, up 1, 2, 3, 4, 5, 6. So I'll end up right there. Okay, because I'm starting where the other one left off. So there's v. And look at my result. My result is I started here and I ended up here. That's 1, 2, 3, 4, 5. 1, 2, 3. So 5, 3. Okay? So you can see it on the graph here. You can see it algebraically as well. Not too difficult. Okay? Scalar multiplication. This is also an operation as well that we've looked at geometrically. All right, so let's look at the scalar multiplication. When we multiply vectors, we remember that we're just putting one, then another one of the same thing, and then another one of the same thing, however many times. So you'll notice here what we end up doing is that if I have a constant c times vector v, I'm just going to go horizontally a units, however many times c is. Okay? So here in this case, v is telling me to go right 2 units. So for v, I'm going to end up going 2 units to the right 4 times. So I just multiply the 4 by 2 and I get 8. Okay? Now, vector v is telling me to go down 6 units. So if I go down 6 units 4 times, that's 4 times a negative 6, that's a minus 24. Okay? Does this make sense? We got it? Okay. Now, does anyone have a guess as to what this is going to do to our magnitude?
Multiply by 4.
Yeah. In this case, it would multiply our magnitude by 4. Anytime you multiply a vector by a constant, it's the same thing as multiplying the constant by that magnitude. Okay? Now, this is useful in keeping our numbers small. If you have a vector that has some pretty large numbers, if you see a common factor, you can make it as a common multiple of a smaller vector and then just multiply the magnitude by that at the end. For example, if I had a vector, let's say I had a vector u that was like, oh, I don't know, let's see, 2500, and actually let's make that, whoa, hang on, too much. Let's make this 2400. Okay. And 700. Okay. I could simply write u as 100 times the vector 24, 7. Right? And then maybe you'll notice, oh, that's a Pythagorean triple. What's the magnitude? If I'm doing the magnitude of u, I can simply do 100 times the magnitude of 24, 7. What's the magnitude of 24, 7? It's a Pythagorean triple.
25.
25. 7, 24, 25. Alright, so the magnitude there is 25. So I can just do 100 times 25. Or 2500. I don't have to actually square 2400 and 700. Okay, and then add those together and square root the whole thing. This is a way that we can use this property to help us out. Likewise, if I have a vector, like say this vector v up here, 2, negative 6, let's say we're designing something and the motor that we have installed is going to pull with this force vector. Okay? So the magnitude of my force would be 4 plus 36, so square root of 40. Alright, the magnitude of V in this case would be square root of 40 or 2 root 10. Let's say I need 4 times as much force in order to do what I wanted to do. I could just hook up 4 motors that are all pulling the same amount. And if they're all pulling the same direction, that'll do it. That'll multiply my magnitude by 4. Give me 4 times as much force. Okay? So, that's the idea here of the scalar multiplication. Okay? Now, here's an application, and this is actually going to be a very important application. Alright, it's important that you understand this. And this is one of those things that even those of you in physics, you may or may not have done this. Okay, so take note of this here. We want to find a unit vector in the direction of a vector that we know. Okay? We want to find the unit vector in a direction of v. So let's think about this here. We have, first of all, a vector v. Let's say that it is negative 6, 8. Okay? Now, what's the definition of a unit vector? This is a term that you should know.
It's either parallel to the y-axis or to the x-axis, and it's only one, and it has the magnitude of 1.
Well, there is a horizontal and a vertical unit vector. We have I and j. Okay?
Oh, but it doesn't have.
But those aren't the only unit vectors. What is it that makes those a unit vector?
Vector with magnitude 1.
Vector with magnitude 1. Alright? Is the magnitude of this vector equal to 1? No. What's the magnitude of this vector?
Radical of 36 plus 64, 10.
Okay, yeah, it's the square root of 36 plus 64, that's 100, so we have a magnitude of 10. So, if I know that multiplying a vector by a constant will multiply that magnitude by the constant, okay, the magnitude of a constant times a vector will be that constant times its magnitude. What would I need to multiply by to get it to have a magnitude equal to 1?
1.
Huh?
1/10.
1/10. Okay? If I make it 1/10 times 10, that will give me the magnitude of 1. So I know I need to do 1/10 times vector v in order to have a magnitude equal to 1. Okay? Does that make sense? All right. We're using this property here. Okay? So that means the unit vector, again, unit vector means magnitude equals 1. The unit vector is going to be 1/10 of v. So that's going to be 1/10 times -6/8. And we should go ahead and simplify that. So that would be a -6/10 or -3/5 and 8/10 or 4/5. Okay? So, this vector right here has the same direction as this one, but its magnitude is 1. Okay? Now, a question that you might be asking is, why in the world would we want to do this? Can anyone take a guess?
Because you want to focus in the direction instead of the magnitude.
Okay, maybe we want to focus just on the direction and not the magnitude. What else could we do with this?
Oh, unit circle.
Actually, we will relate a little bit to the unit circle later. That's when we know what the angle and magnitude are and we want to get the component form. We'll get to that later.
It's the opposite.
What if I knew I was going in the right direction, but I had the wrong magnitude?
You need to make it like bigger.
Okay, if I needed to make it bigger or something like that, like let's say here, we knew the magnitude was 10, but I need the magnitude to be 18. Okay?
Divide by 10.
By dividing by 10, now the magnitude is 1, so how do I make the magnitude be 18? I just multiply it by 18. Okay? So by finding the unit vector in the direction of our given vector, then we can change that magnitude to be whatever we need it to be.
Wait, say that again. Why are you multiplying by 18?
Okay? If we want that direction,
You just want it to be the vector to be bigger.
yeah, if we want that same direction, hang on, but
a different magnitude okay, we can divide first of all, or multiply by 1 over the magnitude to get it equal to 1, and then we would simply multiply by the magnitude we want. We can do this all in one step.
Oh, so after.
Okay.
you get to one.
Yeah, after we get it to 1, then we can multiply it by what we want in order to get it there. Okay? You could do this all in one step. Hang on. Multiply by this. So you'd multiply, if to do it in one step, you could multiply by a fraction. You could multiply by the magnitude you want over the current magnitude, or original magnitude if you want to say that. Okay? So now we just have a couple combinations here. Combinations of vectors. Again, this is something we've done a little bit of geometrically, but really the nice thing about this is that the same order of operations applies here as with what we were doing with regular numbers, okay? So I'm going to do the multiplication first, and then I'm going to do subtraction, okay? So I have 2 times vector u, so 2 times 4, negative 3, minus 3 times vector v. Again, if we have 1, 6. I do the multiplication first. So I have 8, negative 6. And I have a minus 3, 18. If you want to distribute the minus with it, it would then be plus negative 3, negative 18. Okay? Just don't do the minus twice. But now we have subtraction. 8 minus 3, we have 5. And negative 6 minus 18 is a negative 24. Okay? Now that we know that, we can find the magnitude. So that's just going to be the square root of 5 squared plus negative 24 squared. Okay? So we have 25 plus 596. Wait, 20 times 28 would be 560, 576. Right? 24 squared. So now we add those together, we get 601. So the square root of 601, I don't know if that radical actually simplifies or not.
24.5.
Okay.
Also, a really, really large number of fractions.
Okay, 24.54. So yeah, you can round to like 2 decimal places, that'll be fine.
Yeah,
Okay.
That's quite large.
Nice. Alright. So again, follow order of operations. If you had parentheses or something, of course you'd simplify what's inside. You could distribute constant multiples. A lot of those same algebraic things that we've done in the past apply here. Now, one other thing here that I want to look at, and this is the direction angle. It's something that we mentioned before, but we hadn't actually done any of these. Okay? The direction angle is an angle in standard position. Alright, so if I have this vector where I'm going over A and I'm going up B, alright, the direction angle would be what? How would I find theta in this case?
Find B over A. Oh, no,
You
use the arc tangent.
Negative sign. Sign.
No, not-
inverse sign.
Not sine,
No? Oh, tangent.
tangent, okay? We'd use the tangent of theta would equal b over a, and then, yes, we would use the arc tangent or the inverse tangent of b over a. Now, one thing that you need to be careful of is watch your quadrants. Watch your quadrants. Okay? Now, here's what I'm talking about. We have vector u. U, if you want to rewrite it in component form, would be 3, 3. Alright, what's the angle there?
45.
It's a 45-degree angle. Yeah, we see it's an isosceles triangle here. Isosceles right triangle. But I mean, if you did the theta equals the inverse tangent of 3 over 3, you'd get inverse tangent of 1 is 45 degrees. Okay? Or what?
Or 135.
No? Come on, it's just the last unit.
What, the inverse tangent of 1?
Yes.
It's also 135?
No. Tangent's negative
Oh.
over there.
I'm sorry, it's 225.
225, okay? Now, how do we know which angle this is?
Oh, you look at the sign off the B and A. If you're positive.
Yeah.
Yes. Look at which quadrant your B and your A are going to push you towards. We're going to the right and we're going up, right? That would be the first quadrant, so it's 45. What vector would have a direction angle of 225?
Negative.
Yeah, negative.
There we go. Negative 3 would have a direction angle of 225. Okay? Be very careful that you pay attention to the components of your vector to get the angle in the correct quadrant. Especially once we start applying this and doing problems where we have multiple vectors impacting something. Alright, that's going to be really significant. We need to make sure that we have our vectors going the correct direction. Alright? So, think about part B over here. We have the vector 3, negative 4. Okay, which quadrant is that going to point us towards?
The bottom, the fourth one.
The bottom right, the fourth quadrant. Okay, we're going to the right and down here.
That's the cosine.
Okay, cosine's positive, sine and tangent are negative. So we're using tangent here. So theta is the inverse tangent of a negative 4/3. Okay,
Wait, why are we using tangents?
Because we didn't have the value.
because of our right triangle here.
Oh, we're using them.
Our components are the legs, so opposite over adjacent.
I didn't know if we were using that one instead or not.
Okay, so on your calculator, what do you get when you do the inverse tangent of negative 4/3?
Negative 53.
Okay, negative 53.3.
0.1.
0.13.
0.13, okay, so we'll do 1 since it's an angle. Alright, now to give this as a positive angle in standard position, we would do what?
Add 360.
Yeah, add 360. Alright, to get a positive coterminal angle, and that gives us 306.9 degrees. Okay? Now, if this were the vector negative 3, positive 4, I would have wanted the angle in the second quadrant. So I would have done 180 minus 53.1, and gotten our 126.9. Okay?
It's going to be degrees in the bracket.
Yeah, we're gonna use degrees on most of these here, so, but just to illustrate here, negative 3, 4 has a theta equal to 180 minus 53, so 126.9. Alright, so pay attention to those components and which quadrant it's pushing you towards. Okay? Any questions about that? That's a really easy thing to overlook. So when you're looking at direction angles, make sure you pay attention to that.
Wait, Mr. Harrison, I don't know why I didn't see that. How'd you get, 126? I thought you,
So I was saying, if the vector was negative 3, positive 4, our direction angle would be this one instead.
oh, you just,
Just add nine.
Yeah. So we would be in the other quadrant.
mhm.
Okay? The problem here, and this is why I'm pointing this out, when I plug in inverse tangent of negative 4/3, my calculator doesn't know if it's a negative 4 over positive 3 or a positive 4 over negative 3. They're both just negative 4/3. So your calculator would give you this answer either way. You need to interpret it correctly based on which vector, which quadrant your vector is in. Okay?